Good afternoon. It's Gord Cooke here from Building Knowledge Canada. Welcome to webinar series, the Enbridge webinar series. Today's webinar is called New, Small, Crazy, Smart HVAC Systems for Net Zero Ready Homes. I'll say it's for net zero as well. We'll just take a minute here, give people another minute or so to get caught up, and then we'll come back at you and start our session. So just take a quick second and let a few people sign in. Stacy, you'll let me know when it's appropriate to start.
Yeah, they're rolling in now. You're right. It's a sunny day out. They probably didn't want to have to sit down at their desk.
There you go. It's still cold out though. I see we have 60 or so signed in. We'll wait just a second here. Although we don't want to wait too long because we only have an hour and a half. So.
Yeah, I'd get started now, Gord.
Great. Well, thank you again for those who have just signed in. I'd introduce myself, Gord Cooke from Building Knowledge Canada. We're always pleased to be able to present these webinars fully supported by Enbridge, your energy distribution partner in Ontario. And I have with us two really interesting guests today that I'll introduce in just a second, but and as well Susan Cudahy's on the line, and I'll have her speak a little bit. So today's session in a quick hour and a half is a specific topic regarding distribution of air, and we've called it New, Small, Crazy, Smart HVAC Systems for Net Zero Ready and Net Zero Energy Houses. And really it's about improving the distribution effectiveness of air, and this happens to be one solution to that. And as I say, I'm joined by two really, I'm going to say really important guests. First is Andrew Poerschke from IBACOS, which is the Innovation Building and Construction, I think it is. But IBACOS, most importantly, was one of the first three Building America teams. And for those who don't know, the U.S. took on, in the same way that Canada does a bunch of research, the U.S. took on at the Department of Energy some really interesting research work, and they identified research partners within that, and IBACOS out of Pittsburgh was one of those. And Andrew continues to conduct research in building performance and advanced modeling, computational analysis experience, research on innovative space conditioning technologies. And he's going to talk to us today about one specific one that was done, Andrew, I think it was over 10 years ago, but perhaps 15, that the research first started on.
Yeah, about 10 years ago.
About 10 years ago, thank you. So as much as we know we have a problem, we can turn to our American friends and say, hey, you guys did some research on this. How did that work out? And then directly out of that, we're going to have Rob Beach, the senior designer at RIA, and Rob, you originally were working with Andrew at IBACOS, and we're going to learn when Rob comes on, we'll learn about how they took the research, and I think it's brilliant, took the research and said, hey, how do we turn this into a product that will indeed help the industry? So kind of cool, and you'll see Rob's experience there. Rob, you've been, RIA's a new company, but in this particular field, how long have you been active in this research of HVAC distribution or distribution of air in houses?
Since about 2010, so going on 13 years here. I began with IBACOS and started working with Andrew shortly thereafter, and he and I were tied at the hip for many years, digging into these problems.
Yeah, kind of fun. So both of those gentlemen will be speaking later, but Stacy, I'll turn it over to you just to go through some of the housekeeping and rules of engagement.
Yeah, thanks, Gord. I'm actually putting them all over in the chat as well, the housekeeping rules. So we are going to have Q&A at the end, but we encourage people as the speakers go along to just put those in the actual Q&A part down in your bar down below, it actually says Q&A. And then that way we can capture those questions, and Rob or Andrew or Gord can actually write in an answer if we can't get to all of them. And just make sure that your questions are thoughtful. We're mindful of the time, so we want to make sure that we can get all the questions in as quickly as we can, but we might not be able to get to all of them. So we'll try and capture those after the presentation. The presentation does get emailed to everyone afterwards, so you can just sit and enjoy what you're going to hear today, and it'll get sent to all of you as an email afterwards. And then we do encourage you to fill out the SurveyMonkey link afterwards. That just helps us to do more of these kind of presentations and where we want to take any more of these discussions. And if anyone wants to have the actual written part show up on their screens, they just have to click on that closed captions section down at the bottom as well, and you'll see the live transcript as the gentlemen speak. So I think that's all there is to that part, Gord. So thank you.
Thank you. And we always like to acknowledge, because what a great partner they are. Enbridge has been over the years. And so this is fully sponsored and supported by Enbridge. And specifically have with us today, Susan Cudahy. Susan, unlike Andrew and Rob, you and I have been at this industry a little longer than 13 years. But Susan is the supervisor of strategic builder relations at Enbridge. And Susan, you just had a few things that you wanted to say to folks.
Yeah, definitely. Thanks, Gord. And just a quick welcome to everybody that's attending today. It's a great topic for discussion for sure. And Gord, maybe you can just go to the next slide. We just, instead of our usual safety moment, just wanted to take a quick second to talk about something that's occurring right now. We've had some really interesting weather this winter with a lot of freezing and melting, and it's created some really slick conditions. Unfortunately, the result of that has been that there have been a number of critical injuries that our Enbridge employees have had happen to them on some of the job sites. So it's just a reminder. I know everybody's trying to do their best out there to keep everybody safe, everybody going home at the end of the day. But just a quick double check when you do have Enbridge staff coming to the site, just be careful to do a quick review of the site, make sure that it's accessible from the street to the riser location, and there isn't any wood or building materials, scaffolding, nobody working overhead, any spills or anything that can create a sort of a slip, trip, or fall. And that way, all of us will be able to go home to their families at the end of the day, and hopefully in a very safe environment. So with that, thanks again for joining us for the first of our 2023 webinar series. We've got a great lineup this year, and I'll turn it back to Gord.
Thanks, Susan. And that is an important safety message. It has been a tough winter for sure. And that is interesting. You say this is the first of the year. I'd sort of forgotten that. And we had such fun last year. And thanks you again for sponsoring this year. And Andy and crew have put together a pretty cool session, and I'm very pleased to start off this session. We kind of like to know who's here. We have about 100 people online right now, and Stacy, you kind of like to run a few polls to figure out where folks are from. So let's start with that. If you could just put that in the poll, please, folks. I just came back from Denver. It was, they've pretty much gotten rid of their snow there. So that was kind of cool. I was in Atlanta a couple days ago or last week, and it was flowers were starting to bloom. So a little bit of hopeful sign as to where the weather's headed. Wonderful. So we actually have a couple of folks from the US. That maybe that's just Andrew and Rob. I don't know, but no, there's probably others as well. Always interesting crew from the left coast, from British Columbia. Thanks, guys, for joining. Really appreciate that. And second, we always like to ask what's keeping you busy from day to day. What part of the sector? We always end up with some others. So I'm always interested in what if you could put that in the chat, that would be great. But let's see where we're at. Assuming and knowing that this is, in theory, an HVAC session. Let's see how many HVAC contractors and designers we have on the call. That'll be fun to see. And Stacy will put up the results. Thank you. We just love that builder renovator. Guys, you'll see roughly half the group, Andrew and Rob, you are speaking to that builder renovator group. We do have some HVAC folks on the call, so thanks for that, folks who are coming in. Really love that. A couple engineers, that might be Richard Lay out west that's on there. And thank you all for coming on the call, and hopefully we have a good hour for you. We will run essentially an hour's worth of presentation, and that'll give us 15 to 20 minutes worth of questions at the end. I'll remind you again, it's best if you put the questions in the Q&A, then we can capture them. If you put them in the chat, it's harder for Stacy to capture them and answer them. That is, if we can't get them to all of them. So try to put your questions in the Q&A section so that we can track them and make sure they get answered either in person or later by email. So keep that in mind, please. I'll just click that, sorry. So let's get started. Again, new, small, crazy duct systems for net zero ready houses or homes. And I will just start with a little bit of, have we identified a problem? Is there an issue? So let's start with, what is the issue? And then you're going to find somebody else has done some research on this starting about 10 years ago or a little longer than that. And then there's some solutions, and we're going to show you solutions. It's one of a different solutions, but we'll talk about that. And then try to mention to you some of the resources that are available to you. Andrew has queued up a few places that you may want to go to in terms of the Building America website. As I mentioned, we have some time for questions. And what I want to remind you is that sizing of heating cooling systems has changed. For number one, we, in 2012, a brand new standard, well, a new version of the CSA standard, which is, you'll hear Andrew and Rob speak today about Manual J, which is the heat loss, heat gain standard in the US. Our equivalent to that is CSA F280, very similar. But when it was redeveloped in 2012, we realized that the sizing we'd been doing up till then was rather unrealistic. In fact, systems were dramatically oversized. And so when the 2012 was rewritten, we realized we could have smaller equipment and smaller, less air distribution. Let me put it that way, not necessarily smaller ducts. We also know that energy efficiency requirements came into the code in 2010 and 2012, and that's driven down loads. We now have, of course, as a result of that, improved construction practices. We have new equipment options. And what you're finding, specifically in Southern Ontario, but also in Lower Mainland BC and other places, that cooling loads now dominate airflow capacities in most markets. I say it, most markets in Canada, other than Edmonton, really cold places, cooling loads now dominate in most markets. And of course, we have higher homeowner expectations. So this is a reflection of the problem we're going to show you, is a reflection of these changing heating and cooling loads. And to give you an example of that, I took a 2,275 square foot house in Southern Ontario. And yes, it's Southern Ontario, my apologies, but you would see similar orders of magnitude change in every market across the country. And notice that that same house, if it was built to the 2005 Ontario or National Building Code, would have had a heat loss of 62,000 BTUs and a heat gain of 33,000 BTUs. And in order to drive that heating and cooling into houses or through the house, you'd need roughly 1,200 CFM of air, 1,200 cubic feet per minute of air. And then as we move down through successive codes and all the way down to net zero with a heat pump, and that's important to understand that this includes the airflow required to make a heat pump work in houses. We are now roughly, well, not quite a third, but certainly less than half the load and about half the airflow requirement now required in houses. And you go, well, that's a good thing. It is absolutely a good thing. It means smaller equipment, means smaller duct sizes, but it has a little implication with respect to the distribution of that air, because we still want to move that air around a house. And it's basically half the airflow required overall. So keep that in mind when you hear Andrew talk about their experience in the US. I'm saying to you, we're seeing very similar experience here in Canada. And the good news is we can use the experience of others to help us solve this problem. We also need to know that the HRAI, Heating, Refrigeration, Air Conditioning Institute, recently wrote their residential air system design manual. You'll hear Andrew and Rob both speak of the ACA standard manual D, which is the duct design standard in the US. This is our equivalent, the residential air system design manual. It was just rewritten. Again, I was pleased to be part of that conversation, a lovely committee of folks from across the country who helped that with that rewrite. And in that, we started to recognize higher static pressure allowances. That is new furnace equipment, because of EC fan motor technology, able to achieve higher levels of static. We also a better recognition of supplier distribution options in small spaces and basements, an allowance for rationalization of return grills, a recognition specifically in today's context of low load, high performance home challenges. And you're going to see some of that today. Improved guidance on duct leakage and the use of flexible ducts, and allowance for new equipment options, including higher static and so on. And so useful in this conversation to know that what you're going to hear Andrew and Rob talk about now in this particular solution, one, recognizes the research that IBACOS has done, and two, would allow for the kind of a ducting options that Rob is alluding to. So it matches with our Canadian reference documents, if you will, the documents that are referenced in code. And I just wanted to show you, so I said overall loads in houses have changed. I want to show you what the implications would be on an individual room. And here you see bedroom 3. And in 2005, to properly heat that room, you would have needed 90 cubic feet per minute of air for heating and 49 cubic feet per minute of air for cooling. And if you used a 4x10 register, the ubiquitous 4x10 register that we all see, that would have been a velocity, think of the speed of the air coming out of that vent, of roughly 550 feet per minute. Somebody's going to do the math and say it's a little more or less than that, but it's roughly 550. In today's world, when you think about, you doubled the amount of insulation, you put in much better windows, you made the air tightness much better. And if you redo the loads, that room now only needs 40 CFM for heating, 45 CFM for cooling. Notice how cooling took over the loads in this particular room, windows, the people in the room, and so on. But now to heat and cool that room, the dominant load is the cooling load. But if I deliver 45 CFM through a 4x10 register, I now only have 270 feet per minute of air. And you go, well, isn't that a good thing? That would be lower noise. Sure, there are some nice advantages for it being lower velocity, but from a distribution of air, here's what we need to understand. When we were at 550 feet per minute, look at the right-hand side, that 4x10 register, throwing air, warm air up into the ceiling, onto the ceiling space, creating a pretty nice pattern of airflow around that room. However, when we go to 550, notice what happens. That air, goes down to 350 feet per minute. Of course, it'd be even less at 270. Look now at the distribution pattern in that room, and you start to realize, even with the presence of a return on the left-hand side of the room, I don't get a very good distribution of air across that room. And it gets actually worse in cooling mode. There we are at 550, and we still only had, even at 550, only had part of the room actually doing its job. And so we had stagnant locations. And when we went down to 350 feet per minute, look how poor the performance is in terms of maintaining comfort. It means that everybody would cram over to the right-hand side of the room in order to be comfortable, and we'd end up with warm spots. And even at high wall return, somebody say, oh, you need a high wall return. Even with a high wall return on the left, we don't see very good performance. And Andrew, I would say to you, this was exactly the challenge that you were given. Is that a fair way of putting it? And I'll allow you to share your screen to take over. But Andrew, in the work that IBACOS was given under the Building America program, this is exactly what you guys were asked to consider. Am I fair in saying it that way?
Yeah, exactly. It's that overall trend of improving energy codes and reducing airflow and kind of the implications that had. And, we've kind of mentioned, IBACOS had been doing research on this topic for about 20 plus years, me personally about 10 years. And we'll kind of go through some of those findings, some of the interesting work that we've done, and then how it ultimately led to this idea for a new air distribution system that Rob will talk about. So yeah, again, thanks everyone for joining. I'm Andrew, and we'll get into some of the research that we've done. So the context here that Gord, I think, teed up quite well but I can maybe add just a few elements to that. Is, again, we have this improvement, this steady improvement in the energy codes. And if you look at this chart here, we're looking at kind of a relative energy use index or improvement, and we see a big jump from the 2006-2009 IECC, the International Energy Conservation Code, to 2012. And when that jump happened is when we really kind of began in earnest our kind of interest in research in looking at how new air distribution systems could really benefit the industry. Things had changed, and in order to continue to deliver comfort to homeowners, we had to rethink what we were doing. Then kind of looking to the future, the general expectation is that energy codes are going to continue to ratchet down. Will they be as aggressive as in this chart? Nobody knows for sure, but that's kind of the expectation, that in order to hit kind of these low energy, zero energy targets, things are going to again have to change. So I'll kind of jump through these slides here. Kind of tells the same story, that we're talking about roughly the same sizes of homes, and historically we had a lot more airflow that we were working with when conditioning those homes. In the U.S., usually cooling was the dominant element. So we often talk about it in the cooling capacity. A 5-ton, a 3-ton, and even smaller equipment. And a large house that had 5 tons of cooling had a lot of airflow. And what we've seen is that reduction, roughly having that airflow. And looking forward, that could continue to go down. So that was kind of the context that we did a lot of this research in. Again, these traditionally ducted systems, their performance starts to go down. You're doing basically, you're trying to do the same job with less amount of air. And so, we needed to rethink what that solution could be. Something that we then had spent a lot of time studying was, alternatives, we'll call them kind of smaller duct systems, and there's a lot of different types of systems that fit under that category. And we'll talk about a couple of them here. So one piece of our research that really played a critical role in our understanding of this, this change, this evolving need for new air distribution systems, was this cold climate, at least for the US, a cold climate research home that was located in Pittsburgh, where we evaluated a number of different space conditioning systems, looking at air source heat pumps, ground source heat pumps, and then also evaluating different air distribution, sides of that equipment, looking at kind of the conventional trunk and branch system. We looked at ways to reduce the airflow and simplify the distribution system, and even took it to the extreme of, well, if you have a whole typical kind of builder house, this was a 4-bedroom house, what if you only supply air in 2 locations and try to passively mix that air around the house? How far can you go in terms of simplifying and reducing the amount of air distribution system? And then we also evaluated a small diameter system, and then the Detson variable capacity furnace. And then ultimately, one of the final technologies we looked at here was kind of the version 1.0 of the RIA technology, which we called plug and play. So this home, just a little bit more about it, was a highly insulated home, very nearly hit the kind of passive house standard in terms of insulation and air leakage, triple glazed windows, those kinds of things. So we were kind of looking at what was at the time very much cutting edge home. Today, a lot of these types of technologies are starting to be adopted as more standard things. So yeah, I'll talk a little bit then about some of the results of this research. Like I said, there were kind of 3 primary air distribution systems we were evaluating to try to understand what worked the best. And again, those 3 were kind of traditionally ducted system, a lower volume ducted system, and then this 2-point air distribution with transfer fans. And basically what we found was even with a very low load home like this lab house, you still need to supply some amount of conditioned air into those rooms, and you have to be very effective with how you're throwing that air, how it's mixing, and how it's ultimately kind of returning out of those rooms. This kind of single point of air distribution with transfer fans, there were plenty of periods throughout the year where it just wasn't delivering comfort. So we kind of ruled that out. And that kind of led us down this direction of looking at smaller duct systems. One of those systems that we looked at was the Detson Chinook furnace. And it was one of the first kind of lower capacity gas furnaces that was on the market, really looking at the Canadian market. And that was something that really fit well with this evolution of building codes, where the loads have come down. The manual J, as we do it, that manual J calculation was dropping by roughly half in many cases. And so there was this new concept for a lower capacity variable speed furnace. One of the benefits of that particular piece of equipment was it resulted in longer run times, especially when the capacity could modulate down and continue to gently condition the space without blasting it for brief periods with hot air. And so, again, we collected significant amounts of data and found that there were some benefits to that approach. Just to kind of round out some of the discussion on the kind of smaller diameter systems, we've looked at pretty significantly at how that air actually throws and mixes. You can see a couple of shots that we took where we blew smoke out of a register, one kind of a rounded, more of a jet type register, and then the other more of a traditional diffuser. And if we were blowing the same amount of air, we see kind of significantly less throw. So that air is engaging less in the room. And here's another way to look at it, which very much mirrors the slide Gord showed earlier that shows this severe stratification, where if you're supplying warm air, hot air into a room, and if you look at kind of the levels of temperature throughout that room, a traditional diffuser with these lower quantities of airflow just doesn't mix the way that it would have 10, 15, 20 years ago. And we were, in this research, we were looking at high sidewall diffusers, which are maybe more common in kind of the US market. But it's a concept that we've tried to push and really brought to market with the RIA system, where, instead of using a floor diffuser, we're actually moving that up to a high sidewall and trying to throw and mix that air throughout the room. So again, in this kind of CFD, computational fluid dynamics simulation, we were showing a significant difference between those two approaches. So all of that kind of research, which there was about a 5-year period where we were evaluating these different test systems, and we were doing research nationally as well, looking at passive houses, looking at very tall townhomes, all sorts of different building types, and really identifying some of the issues that were going on with this reduction in airflow. And, it was becoming more and more of a challenge to really adequately deliver comfort. And so all of that led to this Building America project, which we called the plug and play duct system, where we really tried to distill a lot of that learning into a more simplified approach to doing air distribution. So this project, this was again a kind of US Department of Energy, Building America funded project. We really sought out to develop a more simplified duct design method. The manual D, or the RSAD Canadian design manual, is really designed to accommodate a very broad range of duct systems. It uses many different diameters of ductwork. It could be an 18-inch return duct or a 5-inch supply duct. Many kinds of fittings, diffusers. It's a lot of complexity that is ultimately simplified in that design process. And we thought, well, hey, what if we simplify the duct system even more? let's make it 1 or 2 duct diameters, 1 or 2 types of fittings. Can we actually simplify and improve that design process? So that was one of the objectives. We obviously wanted to quantify the performance, and we did that through a lab house testing and additional building energy simulations. We tested different duct options. We were trying to figure out what's the best solution. Is a smooth, rigid PVC pipe, is that a good solution? It offers less flow resistance, but there are other disadvantages, such as it's more difficult to install, a lot of rigid piping. And then also there were code questions about using a lot of plastic in a building. And we'll talk about that a little bit more as well. Then one of the kind of final objectives and benefits of this approach was to actually reduce the amount of labor required to install this equipment. We were facing pretty severe labor shortages, especially skilled labor. And, builders and HVAC contractors were looking basically for ways to do more with the labor they had, with the shrinking kind of labor pool that they had. So again, by simplifying the system, simplifying the installation, we thought we could improve that labor picture. So we kind of got to work. We did a whole bunch of testing, both kind of in a lab scenario and in the real world, where we were blowing air through different pipes, taking a lot of measurements on static pressure, on airflow, and trying to really figure out how we could rationalize this in the best way possible for this simplified plug-and-play air distribution system. We installed this in that same lab home that I referenced before. We ran it through a couple of different heating and cooling seasons, looked at, again, things like static pressure. We were using that variable capacity furnace, and so we could actually ramp down the airflow to be quite low, but because we're using this smaller diameter, in this case it was a 2-inch PVC pipe, we were able to still actually mix that air quite well within the rooms. Related to that, we did extensive testing of different materials to look at the impact on static pressure and to understand if there was a better relationship between bends and elbows and straight duct. And one of the kind of fundamental principles of airflow is that the static pressure loss, which is kind of how hard you have to push that air to get it through a duct system, is very, very much tied to the diameter of that duct. It's actually kind of to the 5th power of the radius. So in the chart on the right, we see the difference between the static pressure loss associated with a 2-inch versus a 3-inch duct. And it's significantly less static pressure loss. And so that kind of led us down this path of looking at kind of a sweet spot of maybe a 3 or 4-inch duct, because that offered reasonably good airflow without some of the static pressure penalties that going even smaller would imply. That kind of design methodology, we started to distill a lot of that testing down to kind of a simplified calculator. And at the time, we were thinking, maybe it was as simple as just counting the number of ducts that you need to go into a room based on the supply airflow requirements. A designer would do that kind of manual J load calculation and then do that air distribution system design. And we thought, maybe they can just pick the number of ducts based on that airflow. The testing that we did basically said, no, you still got to think about bends and elbows and fitting losses. That's all important as well. So we learned a lot of these lessons and kind of through this research really understood the fundamentals of how air was working with this type of system. I'd also mentioned something that kind of became a bit of an inspiration while we were working on this was the PEX plumbing systems that were on the marketplace, and the way that they can come to a home run manifold, which is one way to install a PEX system. It can be trunk and branch, or it can be kind of a home run distribution system. And we saw some benefits when we looked at that home run central air distribution manifold some benefits with how that airflow was actually balanced through the system. So wrapping up that work, these were some of the kind of high-level conclusions, and I think we'll send out a link to that report if anyone's interested to kind of learn more about what we did. But ultimately, we were able to deliver on the performance and comfort objectives that we had laid out. We were able to maintain comfort pretty nicely in that test home. We had identified various barriers to commercialization, kind of largely around the code requirements. And I would say at the time, we didn't maybe fully realize the potential product that this could start to become, which is what Rob will talk about. And then, something else that we became more aware of, which is it's kind of interesting looking at the slide that Gord put up. It seems like in the Canadian market, the difference between cooling and heating airflows is actually starting to balance out, while in the US market, to some extent, the opposite was happening, where cooling again was becoming more and more dominant. Glazing was really the main driver in these load differences. And so, we now have this challenge of cooling loads being more extreme and more dominant maybe than heating loads used to be. So then something else we were still intending to do was use a rigid or semi-rigid plastic duct, which again, had these kind of code implications. And, we engaged with UL, the Underwriters Laboratory, and they published the air duct code, which is UL 181. And there's a lot of strict fire and smoke development requirements in that code language, as well as structural and air leakage and various things that having a large PVC duct or any sort of solid continuous plastic pipe would have never been able to fully comply with that code as it was written. And so that kind of led us eventually down this hybrid path where we utilized an off-the-shelf UL 181 approved duct and then focused on the benefits that plastic connectors could actually bring to market. So we worked closely with UL to identify the best way to actually test those plastic fittings, and then ultimately, found a path to code approval for the product. So kind of at the conclusion of this, we actually started engaging with a US manufacturer, with Carrier, to further develop the technology with the intent to eventually commercialize it into a product. It felt like, there was a lot of potential here, the labor savings, the improved comfort, the overall improved performance. And we thought, hey, it's worthy to really try to put it out there for home builders and HVAC contractors to be able to use in their homes. So that's it for me.
Andrew,
Thanks.
Sorry, Andrew, can you go back just a few slides? It's Gord here. Just go back a few slides to that curve of the static pressure at different diameters of ducts. Thank you. And you noticed, if you may recall, in my one slide there showing the this flows to the bedroom, that sort of standard 40 to 50 CFM. That's why you've kind of drawn it out to that level, right? It's kind of a typical load that we're used to in 5 or 6 inch ducts. And it is interesting to see as you say, that exponential rise in static pressure. So trying to find that sweet spot is kind of interesting. Would you agree that 40 to 50 is kind of what you thought was a reasonable volume of air to try to achieve in a duct?
Yeah. At the time, that was kind of our thinking, and I think the pressure drop that's shown here is per 10 foot of duct. So we're talking about some length of straight duct in that pressure drop. But yeah, 40 to 50 CFM was kind of the target we were looking at the time. And I would say, maybe now we're looking at more like 35 to 40 CFM. Maybe Rob could speak to that when he kind of gets into the technology. But that way, we had a rough baseline in terms of airflow per diffuser or airflow, per supply terminal.
Thank you. And then you can start moving back towards the end again. But the other one comment you made, and I will just reinforce with you that indeed, even in Canada, cooling loads, or many parts of Canada, certainly Southern Ontario and sorry, I was going to say the Maritimes and even Vancouver, you'll find that cooling loads are now, in terms of the amount of air you need, cooling loads are dominated. You see it even more exacerbated, of course, in the US, but we're seeing it too, that cooling loads are becoming, because of glazing, and you said it, of course, exactly right, that cooling loads are effectively window loads. 60% of cooling loads come from the windows, and apparently we like to have as much glass as you guys do in the US. Everybody's an exhibitionist these days. Everybody wants to watch everybody else
like that natural light, the daylighting.
Exactly. So it's kind of interesting to think about that cooling load as dominating, but interesting. And so you mentioned that you ultimately ended up working with a traditional flexible duct manufacturer. One of the questions we had, which Richard Kadulski brought up, he forgot to put in the Q&A, but I saw it in the chat. Richard's a fine researcher and building scientist from Vancouver. His question was the static electricity. Is the friction of the air moving through plastic pipes create static electricity issue? Was that seen as part of an outgrowth of what you were doing?
Yeah, that's interesting. I've never actually had that specific question on static electricity. We hear static pressure. That's probably the most common question that's come up, when talking about this. And I guess maybe would the concern of static electricity be that if it builds up enough, it could cause a spark. Right. And if you had a gas-fired appliance, that could be potentially a risk. I don't know. It wasn't actually something that we measured. What was the charge being built up in the electrons in that plastic tube. But yeah, maybe there is something there.
Well, and ultimately you moved away from straight plastic and moved to the flexible duct, which with a wire coil in it. So I suspect at that point it was a moot point, perhaps. But very fascinating. I'm sure people on the call will be interested to see that you tried, because over the years I've had people say to me, could I use like central vac pipe, or could I use and I saw on there it looked like you were using downspouts, gutters and downspout materials. Yep. Even so we've had these kinds of questions and conversations, and you pointed out nicely that there's many different implications, not the least of which would be code requirements. And so thank you for that. And so we'll move over to Rob, and Rob, I'll have you share your screen, but I'll just remind folks that Rob was working with Andrew on this, and Rob, as you mentioned to me, RIA was effectively just an outgrowth of, or at least an extension of, a research company saying, here's a great idea, we should now try to get that into the public domain and make it an actual product. I was very pleased too, Andrew, that you mentioned, and just before Rob starts, you mentioned Datsun, a really good historic Canadian company who was forward thinking enough to say, hey, let's go to the US, find the latest research, and developed, I would say, what they used to call HVAC in a box. So both a furnace, air handler, if you will, that would reflect the smaller loads, and then marry it up to a duct system that represented. And so it's done nicely in Canada. We're very proud of the work that they've done. And Rob, I know you would acknowledge that and say, but then we wanted to change the conversation just a little bit and get us on to something a little bit different. Looks like you're not in presentation mode yet. Can you go to slideshow presentation, perhaps? So on the top bar, it says animations, then slideshow, and just go to the slideshow format. There you go.
Is that better?
Oh, well, now we're seeing your other side of your screen. Well, it's not so bad though. Let's go with that. That's all right. We're seeing both your the next slide, but I think we'll be fine as long as you don't have anything nasty. And there we go. Sort of. There we got her now. Ah, boy.
Okay, I got the right sequence of clicks there.
So Rob, remind folks physically where are you calling us today? Calling in from?
I currently hail from Phoenix. So we RIA are headquartered here in Phoenix. We relocated after spinning off of IBACOS. So it's nice and warm down here. I don't deal with the same 5 tons of heating stuff. We do the opposite. We do cooling down here.
I do think it was instructive, though, just to reiterate, the research was done specifically in Pittsburgh to reflect cold climate housing. Pittsburgh climate, not a whole lot different than, say, a Southern Ontario or or even a maritime climate. Obviously not as cold as say in Edmonton or Winnipeg, but even though RIA is in Phoenix, the research came out of cold climate. So thank you for that. Rob, I'll without further ado, take it away, please.
Thanks, Gord. So I'm Rob Beach. I work here at RIA as a senior designer, and I worked with Andrew on a lot of the research that he mentioned. And really RIA was a distillation, or a, you know, kind of a result of a lot of many years and a lot of different things kind of coming together into a simplified solution. Really focused on some of the, you know, changing codes that you talked about, and trying to create a solution that's simpler as well, because we're dealing with an industry that's very much all over the place. So really just trying to capture, you know, all of the lessons learned looking at air distribution, and building a product solution around that, and addressing a lot of the issues that have come up over the years in the research, in particular, how to do duct systems when you don't need as much air. And RIA really strives to, you know, create products that address and capture those ideas. Our tagline is comfort by design. You know, we use design and we use the product technology as a focus to create comfortable homes, but also in a way help our you know, builders and contractors, you know, manage that complexity through, you know, good process and good product design. Oops. Let's see. There we go. So what is RIA? You know, it is born out of research, and it is an engineered distribution system with, you know, we seek to improve comfort, you know, and have practical benefits, so that it's a valuable solution to people who are building homes and doing HVAC. And so we have a lot of goals, but ultimately it comes down to comfort, and ultimately, you know, having something that is useful and easy to use and good for the contractors and the builders and ultimately the homeowner. We've gone over the history, but this slide just kind of illustrates that in a bit more detail. You know, out of IBACOS, you know, working in this world for many years, going back to the dawn of the Building America program, and probably even a little bit before that. And as things came to light in, you know, around 2016, it just started to become something that we felt like the industry needed a product. And at the end of those plug and play projects, it was like, well, we have something that really works from a design and in the standpoint of you know, engineering and comfort performance. We thought something that would work for these types of low load homes, but we didn't really have a way to make it happen in the industry or in actual homes. So hence, essentially, RIA was born. Our initial partnership was with the Carrier Corporation, and they took us through some very important work to kind of solidify those ideas and really proof of concept, a real product solution. That's where the parts themselves were kind of solidified, some of our code compliance work and you know, fire related things, as well as some very important decisions about working with all types of equipment, being less focused on a specific high velocity system, but something to be a bit more applicable to a broader market, and using off the shelf or any equipment, and really focus just on static pressure. At the end of that relationship, we kind of felt like we had a lot to work with, basically, as a company, and hence officially RIA was born as a company to essentially commercialize this tech. We engaged in a series of pilot homes across the country, acknowledging the diversity of a country like the United States, and really needing to really test this system across climate zones, across different types of trade bases and markets, and so on and so forth, and starting to manage that complexity and build a kind of a business to serve the entire country, and even now Canada. So there's a lot of continued testing and evaluation specific with the RIA product in a lot of homes. So there was additional data gathering. In fact, IBACOS continues to be involved in some of the more true R&D stuff that we do. And now, after engaging with 8 of the 10 largest production home builders in the US who are actually investors in our company. We're in a kind of production environment at this point, and growing. So just to recap, we established in 2019, our CEO, Alan Lane, is a home building veteran. He brings a lot of the practical expertise to the table for us to be able to take, while me, the nerd in the room who's interested in engineering performance, we also have the practical, considerations of engaging with builders, and actually being cost effective and being productive in an environment like that. So we've really kind of built a team of experts that know the ins and outs of all the various HVAC trades and just distribution, so on and so forth, manufacturing, and brought that to our team to help us, serve the industry in a way that's going to maximize our chances of success. The question is, why RIA? And I think the lead up to me talking was really why RIA is, well, homes are becoming more challenging for forced air systems. And RIA is really born to address some of those challenges, specifically bringing ducts and conditioned space. There's a lot of things that our product is designed to be able to address. Frankly, traditional HVAC systems, some of we didn't put that slide in there, Andrew, but it hasn't changed that much since air conditioning was invented, frankly. And it just really took a fresh set of minds at IBACOS and now RIA to really address it and create something that's going to kind of be future-proof in a way, or help builders meet these changing codes. I'll say that, the codes, I think a lot of builders look to as a barrier. RIA kind of thinks of ourselves as a way to overcome those barriers and help allow the codes to move forward and really tighten the screw on energy efficiency in an efficient, practical way for builders. So our product tries to kind of strike a balance between that performance that we're aiming for with low load homes, but also some of the practical considerations. Yeah, here's just a basic list of its features, and they're really born out of some of the many things that are identified over the years in the research, specifically small diameters. I mean, that's pretty basic. It fits in walls. So when bringing ducts and conditioned space, one of the biggest challenges is bringing bulky things inside the architecture. So the small diameter solves that. It works with any conventional air handler. I think systems like Detson and Unico and SpacePack, they work with high pressure air handlers, and ours is set up to work with anything. It's a static pressure driven design process, and it's able to be tailored to any equipment. The home run layout is an advantage in its simplicity. We kind of simplify the SKUs. We simplify the splits and the fittings and the smorgasbord of things that your typical HVAC contractor has to manage, both from a design and installation standpoint. And we kind of distill that down. It's a home run system. Everything runs out to the registers. It's easy to control that airflow with our integrated dampers. Air leakage is a big deal, especially when you're trying to hit ambitious energy targets. Our snap fit connections were born out of that requirement to make a quick to install system that's also effectively air sealed when it's installed, with essentially minimizing labor to have a high quality connection. The adjustable dampers are very important, in particular when you're dealing with things like changing loads between seasons, but also the desire to really create a comfortable home. The damper integration is a very important thing that we included as part of the system. And of course, the simplified SKUs help a lot. I'll also say, specific to low load homes, your module of air per diffuser goes down. In some cases, you have rooms with such a low airflow, the amount of quantity that you need is handled by a very small duct. Now, our system, from a design standpoint, we don't up the diameter anymore. What we do is we just add more ducts. And that has an advantage in low load homes because you're able to supply smaller amounts of air at more points. So the mixing and the throw and everything is a bit more integrated into our system so that you can get the air across the full footprint of the house with this smaller module there. Now there is some real value, tangible value to RIA, specifically the speed that it goes in. I think builders have to deal a lot with, the changing codes, and it's a challenge to manage that change. RIA as a product system tries to make it easier to, what we call essentially future proofing. Builders are chasing HERS points. They're trying to manage this changing landscape of codes and the way homes are built. And that pressure makes it difficult. And so RIA, with the kind of, breadth of what we're trying to do as a system, is making that easier. We can reduce the tonnage. We can also help in certain incentive situations. I'm not familiar as much with the Canadian things, but in the United States, we have something called the 45L tax credit. And it's expensive to get with some strategies, spray foam attics, so on and so forth. Ducts and conditioned space is kind of the lowest hanging fruit, but it's a challenge. And so our product really tries to address that and provides value for those builders who are really seeking to bring ducts and conditioned space. Just a little bit about the product itself. Andrew mentioned the UL 181 process that began with our relationship with Carrier. We engaged with UL, and they actually helped us kind of identify a set of tests that would be built into the UL 181C standard. You're not able to do the full battery of tests that 181 does on a duct, but the fittings can essentially do a subset, and specifically 2043 is the smoke and heat release test, is something that we pass. Another would be an air leakage test. So there's a pull-out test, so it's a robust fitting, and also what's called a heat soak test, looking at kind of the long-term durability of the assembly, because it's a new assembly, and we needed to have something that we could wrap around in terms of a code compliance standard focused on fire and whatnot. And 181 was the model, really. So you can see here, it lists that out. It's a series of snap fit connections. They go together very easily. That's one of our real advantages, is just how easy it is to learn to put together. There's less fighting with the product by the trades themselves. And as a point of advice, I think, to anybody trying to create a product, is making it easy for your users, the people handling is a real benefit. I think just having something that is easy to do has a real value to the actual people holding that stuff. You'll notice on the right, we have our diffusers, or I guess you call them boots. And you'll notice there's an integrated damper. So the damper is accessible at the face, and when it comes to dialing in the airflow for a specific room based on comfort requirements, you're able to do that at the face. And of course, anytime there's a comfort callback or a complaint, you're able to address it a bit more easily with how we kind of do that. The system is constructed from a manifold in the US. It's primarily ductboard. It can also be done out of sheet metal. And our fittings kind of just install integral to that box. So it's basically a compact box located in the closet. The shop drawing put together by the HVAC designer. And they follow standard methods for constructing that ductboard, using the staples and tape and 181 and all that. In some markets, we're using 1.5 inch, but predominantly it's a 1 inch ductboard located entirely in conditioned space. Here's a rendering of our diffusers. They're actually changing, but there's two styles. There's a ceiling and a sidewall. The sidewall diffuser has a real advantage of throwing air over the occupants. We look at, the product specification as, both to get air all over the house where it needs to be, so it's, fully entrained, but also, they need to look nice, they need to be easy to install, and there needs to be, specifications about how they go in. It's a UV stable plastic, it's ABS, it's kind of strong. That's kind of a question we get sometimes. There's some pictures of the diffusers in the house. I would say one of the lessons learned that we've had is the challenges in housing, in particular, getting these things coordinated and the aesthetics. You know, coordinating with multiple points of distribution now instead of a single point with the lighting, for example, and working with the architects. It's always a good idea to work with people early on in the process from a design standpoint to get things to work well. And we're finding that's absolutely the case, and perhaps more so with RIA, because we have goals related to performance and comfort and all these things. And we need people working together to really make that happen. So here's our kind of process step by step. Gord mentioned Canada, you guys have your CSA F280, you call it. And in the US, we use the manual J. It's basic heat loss calculation for sizing your stuff. We require that, and in most cases, it's required by the code, if not all. And then the manual S as well, which is how we match up that equipment. It's a very important step for us because that airflow and static pressure considerations related to that piece of equipment are supremely important. Now we have basically an augmented manual D process for RIA, which takes the data from our fittings and directly uses them in the airflow calculations. It goes a bit beyond what you would have in your basic manual D, but ultimately it solves the same equations and gives us a static pressure estimate, including the balancing dampers. The RIA Verify then is we understand, as you know, the realities of design is trying to, you know, get a good stab at what the actual house is going to be, but we know we have a flexible duct and we have a situation where things can change. So we have a robust commissioning process that we require our contractors to do, which ultimately tests and balances that system. We feel it's an important component because, you know, it's a good thing to have a design, but it's also a good thing to verify that design and make sure it's actually functioning. And instituting a feedback loop through reporting. So in some places across the country, the code officials like to see this stuff, but that report of what actually happened in that house that was built is something that we share around and make available to the people executing these processes, the builder, the contractor, and the designer themselves. So the designers can use feedback from the field as an important mechanism to improve their designs and understand, you know, how the decisions they're making and the assumptions they make as designers might actually be happening, and ideally get into a situation where they're making improvements. So the technical process, this is where I get really excited, but you know, static pressure is really how we drive everything. A big question we have is, how do you manage small diameters? Well, with us, we just add more ducts to essentially relieve that pressure. So our module of airflow does stick to that 30 to 50 CFM range typically. So you keep that under control and you do a good design, so that static pressure is really going to drive it. We look at the equipment as defining the limits of that stuff. So for heat pumps in the US, I'm sure it's the same in Canada, it's 0.6, and for furnaces it's 0.8, right? But we adhere to the manual J and manual S for those guidelines, and our system can be sized to accommodate, focused on static pressure. We're a big advocate of central returns. It is not something that we enforce, but it's something we recommend. We feel it's a great solution for low load homes. You know, traditional systems with a lot of air going into a room, obviously a door undercut or a very large transfer grill are not ideal. So ducted returns can be really required. But with these lower load homes and with RIA, we really advocate for the central return, and we have a lot of discussions with HVAC contractors and builders about how they work and getting that done. And it allows us to alleviate some of the pressure to kind of optimize and value engineer some of this stuff. So we spend a lot of time helping the industry understand the system as its whole, not just supply and return, but how they all work together and how there's different trade-offs. And central returns helps us. The room CFMs, you know, we as a design-driven process, it's an important consideration to match what the designer said, how much air I needed. So really working and developing easy ways for the contractors to balance the system is very important to us, and something we spend a lot of time, working through with the contractors. We do a lot of training. As you all know, if you're a builder or anybody in the industry, the skills are kind of across the board. So we, as a company, have to spend a lot of time as an educational component, helping with these more technical concepts of static pressure and making it easy for folks. I'll just end here with just a summary of, we have done extensive monitoring, kind of side-by-side comparisons of our system across the country, and continuing on what Andrew and IBACOS were doing with the lab home in Pittsburgh, we've continued that culture of using pilot homes to really assess and continuously assess what we're doing, because we work in a very large country, and there's a lot of different climate zones, and there's a lot of different things that can happen when you jump state boundaries, when you jump municipalities, et cetera. So we went across to a variety of markets and installed our system in a kind of pilot phase. And we achieved great success, both from just demonstrating how process-driven, simplified systems are able to produce comfortable homes. And it's not good enough for us to sell a lot of parts. We want to sell a lot of parts that generate these comfortable homes, and that's really a driving force behind the technology that we're continuing to develop. I would say that's about it for me. Yep.
Yeah, and thank you, Rob. Maybe I'll ask you to stop sharing, and I'll put my screen up. But as we're switching over here, I would just let me get my, where'd I go? There we are. I thought a couple of points I would just highlight quickly. Let me see here. Am I sharing now? Yep, good. Let me see if I can get to that. It's all right. Yeah, I need to get to the presentation. Why won't that go away? There it goes. Just get rid of that. We got it there? Good. Yep. I just thought I'd highlight a couple of things. You had said more vents per room, which initially builders say to me, I don't want more vents. But in fact, if we're talking low load and smaller, we actually probably do want. I mean, the chance is that our code historically always said bathe the outside windows. Well, if I've got windows on 3 different walls, that means I need 3 vents. But for heating and cooling, I only need 1. Maybe we should go back to more vents. So I thought that was a pretty interesting concept. Have you gotten pushback from builders on the number of vents per room?
To some extent, I think they understand the reasons why more vents is actually a good thing for mixing air, but they're concerned with the aesthetics. It's usually a reaction, not really a barrier. They look at, a bunch of vents, like it does fly against the wisdom of, I don't need to wash windows anymore necessarily. But with the low airflows and the low throw, you need to get them a bit more into the space and have them a bit more distributed. I would say that it comes down to coordination with things like lighting and making sure, we got a lot of stuff up there. There's a lot of stuff up there now, but we find through coordinating and making sure, the architect himself is helping align things in a nice grid and in a way that they're even, the contractor takes care to evenly space them and so on and so forth. It hasn't really been a barrier. It's something that they're like, it's more of a curiosity, I would say.
Fair enough. And it may interest you, you did highlight a couple of differences, or at least folks on this call will go, well, we don't really have a problem with ducts in unconditioned space. We haven't historically put our ducts, well, I mean, we do, we put them in garage ceilings and so on. And you mentioned HERS score, which most on this call will recognize as the US equivalent, if you will, to the Energuide rating system of houses. So we wouldn't necessarily see the same improvement in energy modeling because most of our ductwork is already in conditioned space. That said, still really powerful to think about improved comfort, reduced heating, cooling loads. But the duct leakage you might find of interest. We have a requirement, at least in the Ontario Building Code, to seal ducts. It's just a prescriptive requirement. No requirement to measure ducts yet. There is going to be a move afoot in our Energy Star program, in our net zero program, to not require duct sealing, but getting extra points, if you will, brownie points for doing duct sealing. It's something that I've long advocated for. Our ducts, and we've probably measured as many as any, are in the, used to be 20 to 25% duct leakage. Now we're finding 15 to 20% in a one that's done to code, still 15 to 20% leakage. And pretty powerful to know in a low load home, you want every last CFM coming to the rooms. And so to know that this system is low leakage is pretty cool. I also wanted to highlight for those in the call, because you mentioned the typical supply side static that you'd, for those who are kind of techie on this call, did you say 0.4 is sort of a typical design static on the supply side?
Yeah, it kind of runs the gamut, and ultimately the designer's making that decision. But 0.4 is a reasonable average. I would say you can actually go a little lower, but you have to compensate with more ducts. So there's a bit of a value engineering that goes on.
Sure.
And we look at it from a total standpoint. So supply, return, coil, filter, and the equipment limits themselves, and specifically what the manual J says in terms of what I need for airflow. That kind of all drives what ultimately you end up with.
And I just wanted to make that point to folks on the call. That was the important element of that new residential air system design manual. There didn't used to be good direction as to the limits of that manual, but the historic was design the entire system to 0.5, return, filter, air conditioning coil, and supply vent at 0.5. We were finding that to be a little unrealistic in today's systems, given that filters, almost every filter you buy is 0.2. And the new residential air system design manual has put a limit on the duct pressure of 0.8, a total 0.8. So that would be your return, not counting the coil, you'd have available to you 0.8, which tends to match, as you will well know, Rob and Andrew, tends to match what new furnace manufacturers, or at least new equipment from Carrier and others. Andrew, I think that would be your experience as well, that the Carriers, Lennox, Trains of the world, their equipment is good up to 0.6, 0.8. Is that fair?
Yeah, definitely. And like you said earlier, it's the EC motors that have really enabled that. They can maintain airflow at a little bit higher static pressure.
Right. And so I just wanted to highlight here. So we go to smaller duct and smaller grills, take that 30 or 40 CFM, but continue to push it out at, say, 550 feet per minute. And you've advocated high wall, which I've always found, following the research, Andrew, that you guys did in Pittsburgh, a cold climate, and you started to advocate, well, of course, cooling should be high wall. That's pretty standard. But when you think about heating from high sidewall, pretty interesting, right? And that's basically what you guys found, that in fact, to some extent, you're better to distribute your heating from the high sidewall. Would you just comment on that, Andrew? Is that, I just want to validate that that's what you guys found.
Yeah. No, that was an area, of a lot of research. And, I think there was maybe a comment in the Q&A about comfort and is air blowing directly onto people, and that was something that we wanted to kind of solve for that challenge. And so a high sidewall, typically, unless you're putting your hand in the air, you don't actually feel the direct kind of velocity of that air. I would say the one caveat is that, you still have to be aware of things like slab on grade construction in a cold climate. That slab is going to tend to be colder. And so, there's some things like that you got to be a little bit more aware of if you're using a high sidewall, but generally speaking, they can be quite effective.
Yeah, and as you say, they're at least not, they're up above the airstream. Although it turns out I was in Atlanta last week, and apparently they're building for giants because they had 12-foot high ceilings. I don't know exactly how tall people are getting in Atlanta, but it obviously vents up there, we're not going to be blowing on people. So I just thought it was pretty interesting. As I say, I've been following that IBACOS research for years, and I've been advocating. Those on the call, builders on the call, will know there's some advantages to being up and out of the way, right? No curtains, no furniture to worry about, no Cheerios, as I've learned with my grandchildren, lots of Cheerios in the vents on the floor. So pretty powerful to think about those. So I just wanted to highlight that. And then I would just say, Summer, speaking of grandkids, those are mine there, but just a bit of a summary before we get to questions. Energy efficiency, that idea of the benefits of energy efficiency, which we get to with net zero, safer, healthier, more comfortable, more durable. However, it does present some challenges with respect to forced air distribution. And specifically, as you kind of alluded to, there's in-floor heating, there's mini splits, there's lots of things that we could be doing in low load housing. But if we're going to stick with forced air, then we have to think about that lower air volume. Can we get the proper mixing or distribution of air to meet those comfort expectations, and to think about rethinking those old rules? And that's essentially what IBACOS and the Department of Energy in the US has helped with. The nice part is this research has now been done, and we can, and of course, we're going to want to do our own pilots and think about it. But this idea, and Andrew, you mentioned it, of throwing that air, thinking about the throw of the air to improve that distribution is really powerful. And that does leave you with these opportunities for smaller ducts, smaller grills, interior wall grill locations, and ultimately getting this idea of take that efficiency, but also add to it the comfort and easier to install. So I think hopefully that summarizes the conversation. The good news is we have, so I'll stop sharing, and I think we'll just go straight to screen. And let me just do that. And we'll just take some of those questions. If you guys are okay with it, I'll kind of read them out, but we'll start with that. Miles asked right off the beginning, and perhaps I'll answer this one. Are ceiling fans practical for low flow problems? And sure, we could start adding extra distribution. I think we would say you'd hate to put in a forced air and then have to put in another forced air system. So ceiling fans can be very useful, specifically in cooling season. But the premise here was, let's solve this from the get-go by doing forced air. So I thought that was pretty interesting. And then Miles did say as well that smaller diameter ducts leads to higher flow, but higher fluid losses. And I'm not sure exactly what he's alluding to, but I think, Andrew, you could speak to the science of this. That was the premise of the research, right? Was to find the sweet spot.
Yeah, exactly. I mean, you're right. You know, the smaller the diameter, the more static pressure loss. But one of the things we really tried to do was optimize the fittings. You know, if you look at the typical duct design chart, the fittings typically make up the highest component of the overall static pressure loss for a duct system. And so what we tried to do is actually optimize those as much as possible. You know, there's little roundovers. We did a lot of CFD and testing and things to make them as smooth and aerodynamic as possible to help make sure that we kept the static pressure kind of to an acceptable level. You know, and then kind of touching on what you were just mentioning, by making the duct system more compact, bringing it, at least in the US, into conditioned space, and using you know, the interior walls to throw the air versus running a duct all the way to the exterior, well, that shortens all of the ducts quite a bit as well. And so all of those things together kind of meant that, you know, we could still keep the static pressure at kind of that acceptable range for conventional equipment while still getting the benefits of the smaller duct.
Thank you. I love that answer. And then David Burke's our good friend. He said, in Southern Ontario, are we better off with high or low wall returns? I think he's more qualified now to ask in Southern Nova Scotia, from what I understand, where, you know, David's spending some of his time. But David, hopefully you don't mind me mentioning that. But we get this a lot. And I thought one of the most important pieces of the Pittsburgh research was, so tell us about how critical is it to think about return air locations?
Yeah, I mean, that was something we did study. You know, I kind of focused more on, I guess, the supply work that we did, you know, but we also looked at different types of return systems, you know, whether it was a distributed return. I don't know if we ever did a full ducted return to every room, but kind of a key distributed return, or a return on each floor, or just a single point of return. You know, and what we've found is with the very, very, very high levels of air sealing that we had in that Pittsburgh home, the return location was less critical, almost to the point that it didn't matter, just again, because it was so well air sealed. I think in a more typical production home, builder home, you know, with a little bit more air leakage, you know, you would want to be more aware with where you're putting that return. You know, so if it's a heating dominated area, and definitely putting that return either on the first floor ceiling or maybe somewhere in the first floor would have benefits. But you don't necessarily need a return on each floor, especially with RIA, because you're able to supply that air. It's able to mix that much better and overcome some of the limitations that historically a distributed return kind of made up for some of the poor design and installation of the supply duct work. There's a report I can actually send. I can send a link to that we had published with NREL, looking at specifically kind of the home run system and some benefits on the return location.
Thank you. I normally quote you guys as saying it's airflow patterns are best set up by supply. You can blow air further than you can suck it. So worry less about the placement of the return, worry more about the placement of the supply. But David, thanks for that question. We get it a lot. And I sometimes, it gets a bit controversial because I sometimes flippantly say it doesn't matter where the return is. It matters, but it's less important than the supply location, I think, if we could paraphrase. And then Kenneth asked, rigid plastic duct piping is commonly used in many Asian countries. From a Canadian perspective, any challenges with respect to fire in new low-rise housing or larger MERB type buildings? And I think that was really that 181 that you were speaking of, that you've done the work in the US, and that's analogous to our S102 standard in Canada. So we would say we're pretty good shape, at least in low-rise or Part 9 construction, what we call Part 9, which is our residential sector. Any thoughts on that? And maybe I'll put it back to Rob, RIA specifically. Any concerns on fire ratings?
No, I would say we kind of went above what was required just to make sure we were really addressing that from a codes and fire protection standpoint with the 181C development. With the 2043 tests and the various other tests, we really looked to create something that was robust and not really cutting corners when it comes to the certification from a fire standpoint. In fact, we do a lot of work with code officials as we roll out to new municipalities and things. And that's a question. And it's really like, well, what's this 180? It's usually the questions are, what is this new standard that you guys did that's not in the code yet? And so, no, in short, no, we don't have any concerns. We do in multifamily situations, we are in the process of working through when you're going through fire rated assemblies. That's a different story. So with CRD, ceiling radiation dampers and things, we're looking at boots and diffuser products that will allow the installation into fire rated assemblies. So in multifamily, when you have a drop and that drop is considered an assembly, penetrating through it requires a rated product.
Nice distinction there, that within a fire assembly, we're okay. It's when we're moving through fire assembly that we'd really have to think about it.
Yes. Good. And our plastics themselves are a very high quality plastic. It's a polycarbonate ABS blend with a flame retardant. So they don't actually really burn that easily. And that's a design decision, and it helps with the tests, the 2043 tests in particular. Thank you.
And then Paul, thanks for calling in, Paul. Do users of the system notice that much higher pressure of air, we might call it velocity of air coming through the boots? Would this be uncomfortable? And I think we've answered that by saying high wall up above the, let's call it the occupied space. Is that a fair statement? Rob? I
would say the velocity of air on the skin, I don't remember what the specific standard requirements are, but basically the throw of is designed basically to not be felt. And it's kind of tailored in such a way, I think we say 20 feet of throw on the sidewall and 12 feet radius on the ceiling. And basically we have a cold climate ceiling and a warm climate. So the warm climate for cooling dominated places like Florida, Texas, they're going to throw kind of horizontally across the ceiling, and that air falls. With the cold climate, which you'd have in Canada, it's a bit more of a cone shape going down, but that cone's really designed so that when you're on like an 8-foot ceiling throwing down, that you're not going to create an uncomfortable draft kind of situation.
And Paul, I'll perhaps answer it from a numbers game. I do a lot of measurement of systems in houses. We know ASHRAE guidelines, HRAI guidelines, 500 to 700 feet per minute is kind of the sweet spot from a noise and comfort. ASHRAE would say over 700 to 900, you're going to be into noise situations. The high velocity systems that I measure are typically 800 to 1,000 coming out of vents. And if they're noisy, they're 1,200 feet per minute coming out of supply vents. And Rob, what I'm paraphrasing, you're saying you're in that I'm going to say 500 to 700 feet per minute range coming out of the vent. So well within, I'll say again, well within the residential air system design manual, not much different velocity than what you would have seen in the old days, if you will, before we went to low load. And so getting that velocity back up a little bit, still within noise barriers, but not creating undue draft. So hopefully that helps. And then Janet asked a pretty important question that's important to me. How much dependence can we put on the balancing reports? I think one of the best parts about RIA is the little, you talked about a little damper built into the boots that has this little click, click, click that you can actually set an airflow as opposed to a standard butterfly damper that's really hard to adjust. And then you do have a way of verifying the airflow and providing a report. Rob, maybe you could just speak to that quickly. We have about 5 minutes left and still 5 questions. So just be a little judicious with your time.
Yeah, we understand the importance of balancing the system and matching to your manual J. So that has an integrated damper. There's a limited number of settings, and the software actually calculates the positions from a simple set of measurements. So we're dealing with time constraints of the builder, and we're dealing with a lack of expertise generally. And contractors in the United States in particular, I don't know what it is exactly in Canada, they're just not balancing. And so it's all kind of integrated together. So the design file is actually used directly. And then they kind of commission that system, and you get this record. And that record is then shared amongst anybody involved, and it provides transparency as to the performance, and it helps us address problems, having that information. So the reporting is really important. We have some places, actually in Minnesota, where the code officials like to see those things, and they're helping the broader team kind of get a sense that we did install a good system, and that and it's all kind of tied together with the tech, so to speak.
So it's been a requirement in the Energy Star program in the U.S. for quite a time to have actually balancing, or at least commissioning on a simple level of HVAC systems. It's never been a requirement in Canada. I think all of us on the call would start to recognize at some point we're going to see commissioning come into the code. After all, I'm doing it on my warranty investigations, and frankly, it's difficult to say to a homeowner, yes, you were supposed to get 50 CFM out of that grill, but you're only getting 30, and there's nothing in the code that says you actually have to get 50. It just says you got to heat the room to 22 Celsius. So kind of interesting. So we really like that one. I think this will be an easy one. Robert Cooke, no relation that I know of, although he spells it the same as mine. How many times can the connectors be taken apart and put back together before plastic fatigue? Have we done any of that?
That's a good question. We haven't done a specific long-term test, but you can easily do it dozens of times. It's a very, very robust snap finger, probably over-engineered, frankly. And to this point, we don't have a specific limit because it's never happened.
Thank you. And then, Andrew, we'll go back to you. You kind of alluded to this with slab on grade. Tammy's asking, do you still recommend a high sidewall heating in a basement? And I think you alluded to, you probably do want to get more heating down towards, so you could do low wall as opposed to high wall. Is that a fair statement?
Yeah, low wall would be an option for sure. You know, in kind of a basement where obviously you can't go any lower than that. You know, there's a slab there. But Rob did mention that there is a heating market ceiling diffuser that has a bit more of a conical shape to the airflow, and that does help get some of the air down and mix to the slab level. So that's an option.
Rather than high sidewall, do a ceiling to move that air down. Thank you.
We will also do a low sidewall.
Fair enough. And Lisa's asked, would having heating output and cold air returns at the same level affect anything? I think we've kind of answered, Lisa, and said it's more about the location of the supply than the return. You clearly don't want the supply blowing directly into the return, but they could be at the same level. It's really about the supply that we're looking at, if I could answer that one. The next question is RIA system readily available in Canada. You've done a pilot home, at least in Canada, Rob, and working towards, I know we have a couple of, you've talked to some distributors of equipment. Is that fair?
Yeah, we have representation in Canada, and we are available, but we're in the early days, I would say. So in terms of being able to do a lot of homes, I don't think we're quite there yet. But we are in market, and we have a pilot kind of program set up, and we're beginning those machinations, if you will.
Yep.
But I wouldn't say widely available yet.
Right. Fair enough. And then Mark's asking, have you done the same type of distribution on cold climate air source heat pumps? So that's a great question. Are you aware, Rob, in the US that anybody's applied this A to heat pumps and B to cold climate heat pumps?
We have done all variety of equipment in all climate zones at this point. We've done enough installations in Minnesota where we have both. And it really comes down to, when it comes to performance of those things, it just comes down to the engineering that went behind in specifying those. And we don't see any concerns really working with either. It's just setting up your job correctly.
We are at time. I'll just say David's asked, and we'll answer David and Miles. There's a couple of specific questions that Rob will ask you to answer. I'll just go quickly to my screen and just finish up with literally one slide or two slides of thank you, if you wouldn't mind. So I just do that. And I'll just acknowledge again that we're very pleased to be working with Enbridge, and if you're not on the list to get our quarterly newsletter to keep a bridge of these kinds of seminars and webinars, please do so. And we have an upcoming sessions on April 13th on all the heat pumps are created equally for those who are interested in cold climate. And then we would encourage you to sign up. It's quickly getting sold out. Our spring training camp is quickly getting filled up. So please go to our website, buildingknowledge.ca, and sign up for spring training camp. We're very pleased to be working with CHBA's Net Zero Council on that particular session. And I'll just thank everybody for attending. And Susan, thank you as always. I should put the disclaimer, Susan and Enbridge are very generous to allow us to speak on these issues. I think they would agree they're not endorsing any particular system, but hopefully everybody found this of use. I just love this concept that builders indicated a problem. A research firm took that up, ultimately created a product that then those builders invested in and said, yes, we think this will help. What could be better than that for our industry? So Rob, Andrew, thanks so much for taking time today and putting that together. We really appreciate it. On behalf of Enbridge and all of our participants, we know you brought great value today. So thank you very much.
Thank you.
So we have a couple more questions.
There is, but I think we'll do those. I'm going to say they're pretty specific. Well, David has said, do you feel there'll be ducted returns soon? And the answer would be, you heard Andrew advocate and Rob advocate for central ducted returns. As opposed to returns in each individual room, we'd be better off with just central ducted returns.
Yep.
Yeah, and our spiel on that is you can do ducted. It just factors into the design, and ultimately your static pressure probably costs you some more money. Right.
And then Miles did ask, does the plastic release toxins? And Rob, you had said this is the whole point. This has met UL requirements both for not burning and then when it does burn, the minimal toxins.
Yeah, it's not PVC, that's probably the most, worst plastic in terms of releasing toxin. It's not that. And it's a small amount of plastic. That was one of the other benefits.
Right. Good. All right. Well, I think we'll sign off at that point. Thank you all very much.
Thank you.
Thank you.